Welcome back to Dave Does Math from Home. This is part 2 of our video series on path independence, section 17.3. We're picking up right where we left off. We left off establishing that vector fields are path independent when they can be written as the gradient of some potential function. When you have this relationship, if the gradient of some weird surface is your vector field, then your vector field is path independent, and that will be incredibly useful for us. This one, we tried to create a potential function and it didn't work. We ended up getting stuck in some weird logical quandary here that we couldn't get ourselves out of. So the next really important thing that we need to talk about is when you get a vector field, we want there to be a way to test whether or not it has a potential function without trying to just build that potential function. Building this potential function, hopefully you can kind of tell by the 1/2 x squareds and the c's and everything. Building a potential function involves doing essentially integrals. You're taking antiderivatives of this piece with respect to x and of this piece with respect to y, and like hoping that they match enough for you to combine them into one big function, which can be work. So it's really frustrating to do all that work of taking antiderivatives and trying to match it up together if it's not going to work. So the goal is to come up with some sort of test to determine right from the start whether or not it should work so that we can save ourselves some time. And there is such a test, and it's very clever, and we're going to talk about it. The test is if this thing is the gradient of something, that means that this piece is the derivative with respect to x, and that this piece is the derivative with respect to y. If these two things really did in fact come from the same potential function, that means that the mixed partial should be equal. So the derivative with respect to x and then y should equal the derivative with respect to y and then x. This is stuff that we remember from chapter 15? I think 15. I might be mixing my numbers up. This is stuff that we should remember from earlier when we started talking about partial derivatives. We said that if a function is of x and y, then you have its derivative with respect to x and its derivative with respect to y. And you end up with 3 partial derivatives. You have xx, you have yy, and the mixed partial, the xy derivative and the yx derivative, should be the same, doesn't matter what order you do it in. And we're using that fact to be able to test this thing. So if this piece is the partial with respect to x, then we need to take a derivative of that with respect to y. And that'll give us f of xy equals 1. If this thing is the partial with respect to y, we need to be able to take the derivative of that with respect to x. Oh, I'm sorry, not 1. The derivative of this with respect to y is 0. The derivative of this with respect to x is also 0. If these things match, then you know that they both came from the same function because the mixed partials are equal. If they don't match, the derivative here with respect to y is -1. The derivative here with respect to x is +1. When they don't match, then they cannot possibly have come from the same function. So that's that's the test, the quick test to determine whether or not a function, a vector field, is path independent, has a potential function that can give you these partial derivatives, is instead of trying to integrate it right away, you take more derivatives. You try to get the mixed partial from each piece and see if they match. That was probably a bit of a long-winded explanation for that, but explanation is over. We're going to just do a bunch of examples of trying to determine whether or not vector fields are path independent. So let me get this erased. So some of these things we can just sort of like make up, like 12x minus 3y squared plus 4, comma 8y squared minus 13. If this is our vector field, and I want to determine whether or not it is path independent, if it's path independent, then this first piece is the derivative of something with respect to x, and I want to take its derivative with respect to y to get the mixed partial, and that would give me negative 6y. And if this is path independent, then this is the derivative with respect to y of something, and I want to take its derivative with respect to x, which is 0. These things don't match. This is not path independent. Again, I think the textbook sort of prefers the word conservative. I don't know why conservative was chosen as the word to describe vector fields. I feel like that word has changed since whoever wrote this book wrote it. Conservative is just very like politically charged these days. So path independence, not politically charged, and much more descriptive. So I'm going to stick with using the words path independent. This is not path independent because the mixed partials don't match. So there is no single potential function phi that will give you this as its gradient. Let's try something else. Let's do vector field f is 3y plus sine of x, 3x plus 16y. Let's see if this checks our boxes for path independence. So I need the derivative of this with respect to y to give us the mixed partial, and that would be 3. And I need the derivative of this with respect to x to check the mixed partial, and that would give me 3 also, and these things match. So this thing is path independent. So that's pretty great. We have this really short, really quick little way to establish whether or not something is path independent. If something is path independent, then we can look and find what the potential function is. And finding what the potential function is going to be sort of like what we did earlier with the explosion vector field, where we're going to try and like take integrals of these things or antiderivatives of these things to try and get back to what the original function was. What's going to make taking these antiderivatives really interesting is that normally when we take an antiderivative, we add a constant piece. There's a plus c somewhere in there, just in case there was something in the original function whose derivative became 0. In multidimensional calculus, that concept of something in the original function whose derivative became 0, is a lot more broad. So let's explore that in a little bit more depth, looking at this problem right here. If I do an antiderivative of this, presumably this thing is the derivative of some potential function with respect to x. So let me do an antiderivative of this with respect to x. The antiderivative of 3y with respect to x would be 3xy. The antiderivative of sine of x would be negative cosine x. The thing that may have been here that became 0 in the derivative could be a constant, or it could be literally any function of y. If there's any piece of this function that has just y's in it, that entire piece of the function is going to like drop out and get deleted when we take the derivative of this with respect to x. So that's why this idea of constants, not the constants, the idea of things in the original function whose derivative became 0 is a lot more complex in multidimensional calculus. So we have this piece antiderivative with respect to x, bam, taken care of, pretty easy. This piece antiderivative with respect to x, bam, taken care of, pretty easy. Maybe there was more stuff with y's, we don't know. We can find out eventually, but we have to account for the possibility of some weird stuff going on in here. And we'll do a plus c. So this is what we get from the first piece, antiderivative of the first piece with respect to x. Now I want to do the antiderivative of this piece with respect to y. And I'm going to format this a little weird, so bear with me. The antiderivative of 3x with respect to y should just be 3xy. And that matches, so that's pretty great. I approve of that. The antiderivative of 16y with respect to y should give us 8y squared. I'm going to put that right here. That's both of these pieces taken care of. Don't have to worry about those. I do need to worry that there might have been a constant involved. And I need to worry that there might have been some function of x's that got completely zeroed out when I took the derivative. And I'm going to put that here. The goal of me arranging things like this is to get everything to line up nicely. So like this piece you can see matches. This piece, I have some very concrete evidence that some piece of this needs to be negative cosine x. I can make that match with the other piece because the other piece has some unknown function of just x's. So we can say, bam, these match. That unknown piece from the derivative of y's, that must have been a negative cosine x. These things also, we can make these guys match by saying whatever unknown piece this had with respect to y's must have been an 8y squared. So this is sort of like the big difference between these. This is some function of x and this is some function of y, and the c bits is these things are always things that you can find out. You have to find out. Like this is partially missing information from only the first half of this. This is partially missing information from the second half. But if you mash them together, you can figure out what those missing pieces of information were. So I'm going to say, final answer, that phi of x and y, the potential function for this vector field, is 3xy. That matches, we're good. This bit with f's needs to be a negative cosine of x. This bit with y's needs to be a, oh, there should be a plus there, plus 8y squared. C gets to stay some sort of arbitrary constant. Don't know what that is. I'm never going to care what that is. It can stay arbitrary. So this is where we're at now. We do your partial antiderivative with respect to x. you'll get some mystery piece. You do a partial antiderivative with respect to y, you get some mystery piece. You can piece that together to make the mystery pieces match. The missing pieces, get yourself a nice solid potential function here. That's where we're at. And the first video was 20 minutes long and this one's already 15. So I haven't even talked about the line integral shortcut at all yet. Let me do another example or two of this stuff and then I'll cut this video and then we'll talk about the line integral shortcut that I promised you at the start of all of this. Okay. Let's do f equals e to the y minus 8x cubed x e to the y. Okay. We're going straight for the fun ones. First, the question of is this path independent means I need to take the derivative of this with respect to y, and that would give me e to the y. And I need to take the derivative of this with respect to x, and that would give me e to the y. And these things match. So we have established path independence. So now if I'm going to create a potential function, I need to start doing antiderivatives. So presumably this is the derivative of something with respect to x. So I need to do an antiderivative of this piece with respect to x to get back to what the original function might have been. An antiderivative of this probably looks like x e to the y minus 2x to the fourth plus some mystery function of y plus some mystery constant. The antiderivative of this with respect to y should look like x e to the y. That part hasn't changed. I'll get some mystery function of x in there. That's fine. That's it. That's all I have here. We'll toss in a plus c at the end. So, again, when you organize like this, you can pretty clearly see these guys match. So they're in. X e to the y is a part of this potential function for sure. Here I needed some mystery function of x, and I've got a function of x in the other half, so I can make sure to include that. Minus 2x to the fourth. Bam, that's in, that's accounted for, we're all set there. Here I don't want to say potential because this is a potential function. Here I have the option, the opportunity to account for some mystery function of y, but there isn't one to account for. If this piece had some like y squareds in it or something, if this was like a plus, y squared, then I would have some extra piece of this function that's just y's, but it's not. There's no y squareds here, so this part I don't need. There's just nothing there for me to set it equal to, so that's fine. And I'll toss a plus c on the end here. This is the potential function. Let me do one more of these. Oh, my eraser's getting a little crusty. Let's see if this is enough. Okay. Let's do f equals 8xy cubed 12x squared y squared. So the test is I need the derivative of this with respect to y. That would be 24xy squared. Derivative of this with respect to x would be 24xy squared. Those match. This is path independent. It has a potential function. to find out what that is, I'll do an antiderivative of this with respect to x. So that antiderivative is going to give me an x squared y cubed, and 8 over 2 is 4. 4x squared y cubed plus some possible mystery function of y plus c. Antiderivative of this piece with respect to y should give me x squared y cubed. 12 over 3 is still 4. I can add some mystery function of x if I need it, and I can still add a plus c. So this piece matches, so I can toss that into the potential function for free. Here, I have the opportunity, I'll say potential, I really want to say potential. I have the potential to add some additional function of just x's. I shouldn't say an additional function. I can add an additional piece that's just x's if I need this to match anything from the first antiderivative, but I don't need it to. There's nothing extra in that first antiderivative, so I don't need to deal with this. I have the opportunity to add a piece with just y's if there was anything from the second piece, the antiderivative with respect to y that didn't match. But I don't need that because that's blank as well. So I'll just add a C at the end. I went over 20 minutes. Maybe this computer thing is just much, much better than the camera because I don't have to worry about the computer randomly truncating these files. That's neat. I think this should still be truncated because I want this in small pieces. I don't want to just send you like a 2-hour-long video. So that'll do it for this video. We have our potential function for this vector field. It's pretty nice. No frills, no surprises. So I'm going to shut this down, and then I'm going to make another video where I talk about how path independence actually helps us. So stay tuned.